we're very happy to see you here as usual. I hope that this has become a habit. Now, so today we're very fortunate to have Francesco Ballarin from Università Cattolica del Sacro Cuore in Brescia, Italy. One of the main organizers of the seminar. He's gonna give a talk on regularized reduced order models for control of Navier-Stokes equations. So this is a change from our schedule. Unfortunately, the speaker Silke could not make it. She got sick over the weekend, but we'll have her. We're gonna reschedule her talk later, either later this semester or in the fall semester. So without further ado, I will let Francesco give his talk. Thank you, Francesco, for volunteering, and looking forward to your presentation. Thank you.
Thank you, Trajan, for the introduction. And yes, I'm looking forward to giving this presentation. And overall, the goal of this talk is to discuss a flow control strategy for, say, turbulent flows, and formulated in such a way that this strategy should be characterized by high computational efficiency. And this goal will be reached by means of 3 ingredients that in the following I will report in the title of the slides with number 1, Roman number 1, Roman number 2, and Roman number 3. Let me jump to Roman number 3 because in this session, in this seminar series is on reduced order modeling, and then for sure there will be an ingredient of this recipe about reduced order modeling based on a reduced space. So that will be the ingredient that this community is most used to. But in addition to that, we will have 2 other items to discuss. Item number 1 will be feedback control as a practical way to steer the flow towards a desired configuration. And ingredient number 2 will be regularization techniques as, again, a practical way to handle flows with large Reynolds numbers by leveraging spatial filtering. So I will try in the next slides to give you, for each of these ingredients, a methodology overview, discuss what practical in the sentences above means, and conclude with a numerical test case. So this talk is taken from these 2 references that you see at the bottom of the slide. The first reference is co-authored with my co-organizers, Maria Strazzullo and Trajan Iliescu, and also with Professor Claudio Canuto, and has been currently submitted on arXiv. And this reference number 1 will be the main topic for the first part of my talk that I call part A. The second reference is another work in collaboration with Anna Sanfilippo, Ian Moore, myself, and Trajan again. And this has been published on finite elements in analysis and design. And the second part, this second publication will be in, let's say, the final part of the presentation. The 2 parts are joined together. The 2 papers are different, but the 2 parts are joined together by the fact, by the common framework of using regularization techniques. And I can already tell you right now that actually we'll be using 2 different regularization techniques in the 2 parts. So I will be showing you 2 of those regularization techniques. Let me start with the setting in terms of the physical problem and of the mathematical formulation. In this presentation, all of our all the rest of the material will be on incompressible Navier-Stokes equations. So our model problem are these time-dependent incompressible Navier-Stokes equations And to set the notations, I will call lowercase u, the unknown velocity, lowercase p, the unknown pressure, such that the incompressible Navier-Stokes equations hold. Those are the first two equations in the system. And these two equations are set in a domain omega. And you have two examples of the domain of two possible domain omegas that we will see in this presentation on the right of this slide. So the first, the domain on the top represents the case of a flow past a cylinder. And that's what we will be using for the first part of the presentation. And for the final part of the presentation, part B, we'll be using instead a slightly different test case in which the domain omega represents the benchmark case of a backward-facing step. In these pictures and also in the corresponding equations, you see that I marked some boundaries. Gamma in is the inflow section, where Dirichlet boundary conditions are imposed for some given data u in. Gamma w are walls, where the velocity is supposed to be 0. Gamma out is the outflow section, in which we have homogeneous normal boundary condition. And we assume a prescribed velocity at time equal to 0. Furthermore, to mimic turbulent flows, we will choose the viscosity, which in this presentation will be denoted with nu, to be a small number. That is, we will try to mimic a case in which the Reynolds number is large. I say that we mimic turbulent flows in the sense that these examples will be two-dimensional, so I cannot really say that we are tackling turbulent flows. We are just trying to put ourselves in a setting in which the Reynolds number is large to try and work towards the actual final goal of turbulent flows. So now I have two slides in which I have a reminder of reduced order modeling for this incompressible Navier-Stokes equation. And for this crowd, that's probably well known, but just to set the notations, let me go quickly over these. So our reduced order model is built upon data coming from an high fidelity discretization, which in our setting is based on a Taylor-Wood finite element discretization in space, where I will, when I will need it, I will call with lowercase h the size of the mesh. And for what concerns the time discretization, with an implicit discretization, for instance, an implicit Euler discretization, with time step size that I will call delta t. Again, for the sake of notation, I will denote the discrete high fidelity velocity at time tn equal to n times the time step delta t as uhn. And as usual in this setting, the reduced order modeling is split into two phases. The offline phase, in which we train a reduced basis space by compressing the temporal evolution. So right now, for people in the reduced basis community, right now we don't have a parameter. Our parameter is time. And the reduced basis will be generated with proper orthogonal decomposition. The resulting reduced basis space will be denoted with capital VR, and R will be the dimension of the space. During the online phase, we will perform a Galerkin method over on this reduced space VR. And therefore, we will be expanding the ROM velocity UR, denoting by Cj of time the coefficients in front of the corresponding POD basis Phi. And by carrying out this Galerkin method, we will obtain an equation like this one. This equation I've written it assuming only the space discretization, but then you can, as usual, further discretize this in time, again, for instance, by an implicit Euler. Two items that I want to highlight because we will need to come back to those in the next few slides. This online phase of the ROM will result in a nonlinear problem, in particular a quadratically nonlinear problem, and this can be solved, for instance, using a Newton method or any other nonlinear root finding technique. And for the sake of notation, I will denote with M the mass matrix for the reducer of the space, with K the stiffness matrix, and with Q the third order tensor associated to the nonlinear term. And each of those, M, K, and Q, can be preassembled once and for all at the end of the offline stage. The other item, which is let's say more related to the fact that we are discretizing an incompressible Navier-Stokes equation, is the handling of the pressure. So in this presentation, for simplicity, we will exploit the fact that each POD mode is by construction divergence free, and hence the pressure will drop out. So in this nonlinear dynamical system that you see here, you will only have coefficient C, which will represent the coefficients in front of the coefficients associated to the reduced order velocity approximation, and we will not look for an online approximation for the pressure field. If you were interested, of course, there are other techniques available, for instance, Supermaiser enrichment or pressure Poisson equations, but we do not tackle them in this presentation because they are not essential for the following topic. So now with this introduction, I can move to the first part A, which is from this first publication in collaboration with Maria, Trajan, and Claudio, and is about feedback control and adaptive evolve filter relax regularization. So I will now need to have some slide to introduce each one of these ingredients. So let me start from the first one, which is feedback control. So let's imagine to have a target velocity, which I will call capital U. The goal of feedback control is to ensure that the distance between the actual velocity and the target one decreases in time for almost every time. Or in other words, the goal is to steer the Navier-Stokes velocity, lowercase u, towards a target velocity, capital U, at the very least when time is large enough. However, to reach this goal, one is only allowed to operate on the forcing term F, which acts as a control in the momentum equation. So you take the momentum equation of the Navier-Stokes equation, this is the nonlinear term, and you are only allowed to go and touch the forcing term on the right-hand side, with an expression F that will depend both on the physical velocity and on the target one. So to make it clear, this is not optimal control or PD constrained optimization, in the sense that we are not seeking a control F such that the distance between lowercase u and capital U is minimized. Rather, we will be happy with finding a control F such that at the very least this distance decreases in time. So typically the control that we find will be suboptimal in the sense of the PD constrained optimization term. Where does the name feedback come into place? At least this comes into place in the sense that the way in which we are allowed to change the forcing term operates by quantifying the distance between the physical velocity and the target one at the current time. And therefore, given the distance, u minus lowercase u minus capital U, the system should be controlled or should, let's say, react accordingly. So in terms of the mathematical formulation, I've written the expression of f as f of lowercase u capital U, but actually what I mean is that the first argument will actually depend not really on u itself, but the difference between lowercase u and capital U. And finally, in my first slides, I stressed on these methods being practical. We believe that this is more practical than optimal control in the sense that this formulation only requires adding a forcing term to an existing Navier-Stokes code, while optimal control would require solving for an additional equation for the adjoint variable. And we believe that, let's say in perspective, this could be especially important for turbulent flows. So the immediate question now that one of you could ask me is, okay, this looks fine. Even this comment about being practical seems nice, but how should we actually choose this forcing term? So in our work, we started from an earlier work by Kunzburger and Manservisi, in which they proposed a specific control law that I will be calling in the following Fa of gamma. This control law depends on a parameter, let's not call it parameter, on a coefficient, gamma. And I will skip for now the reading out loud the actual expression of this control, and I will jump directly to the conclusion. So if you choose properly this control law, then you have a guarantee that if the coefficient gamma is greater than some constant m, you have an exponential convergence of lowercase u to capital U. And the rate of this exponential convergence is governed by, proportional by gamma minus m. So for the sake of space, I actually reported here in this blue box a simplified setting of this theorem. So the actual statement would be stated in terms of weak solutions and also give more details about these constants that appear, but that's not essential for this presentation. And now let me try and go and take a step back and give you some more details on how this feedback control law is actually constructed. So if I go back to the expression of this feedback control law, you see that it is the sum between a term which only depends on capital U, which sort of resembles the strong form of the momentum equation, and the sum with another addend, which is linear in this difference, lowercase u minus capital U, and the coefficient in the linearity is this coefficient gamma that we have to choose. This result in itself is a good result in the sense that it guarantees an exponential convergence. However, the bad news comes into the detail of this constant m, in the sense that if you look closely enough, the constant m is the maximum of two arguments. And if you look at the term between the square brackets, you will see that you may have two cases. If nu is very large, that is, the flow is non-turbulent, is very viscous, then the term in the square bracket will be negative, and therefore the maximum will be of the terms in the parentheses will be 0. And therefore, you would be free to choose any gamma positive you like. However, if nu is very small, the value of the constant m will suddenly become strictly greater than 0. And therefore, the good result, the exponential convergence result, is only guaranteed for gamma large enough. While in practice, you would want to have gamma as close to 0 as possible, because this means that you would like to put as low a control as you can. So this was our motivation to propose an alternative control law, which I will be calling with this suffix B, which is a slight variation of the previous proposal. And this slight variation is just an additional term. And this additional term is again linear in the difference between the physical and the target velocity, and requires the dot product with the gradient of the target velocity. With this small modification, then we have a guarantee that up to a constant secant 0, we have again the same exponential convergence, where this time we don't have any constraint on gamma, apart from being positive, and the rate of the exponential convergence is gamma plus C0 times nu. So the good news is that even if nu is arbitrarily small, as in turbulent flows, we have exponential convergence guaranteed even in the case when gamma is equal to 0. Because if gamma is equal to 0 in this term, you would still have the second addend, C0 times nu, that would still guarantee exponential convergence. So in principle, one could prove again these theorems also in the discrete setting. So the previous two results were in the continuous setting. So for the infinite dimensional velocity. In principle, one could do the same also at the high fidelity level, which for us is the finite element at the finite element level. I do not want to read out loud these expressions. I just want, because we will need to come back to those in a few minutes anyways. I just want to highlight that, again, this is a result that guarantees exponential convergence, and you will see that at the denominator of this expression that I have highlighted in red, the denominator is again governed by the same coefficients. For instance, in this second case, the case of our proposed control law FB is again governed by the sum between gamma and C0 times nu. And that's not surprising because of the relation between the infinite dimensional case and this high fidelity discretization. So I will come back to this expression in a minute, but before I go further, let me show a numerical test case just to convince you that our proposal is good, or let's say even better than the original one. So in this numerical test case, we have this flow past the cylinder. The target velocity capital U is time independent and equal to the Stokes solution. We have a viscosity nu, which corresponds to a Reynolds number of 1000, and we will try two different values of gamma, gamma equal to 5 or gamma equal to 1. So on the picture that you have on the right, you have a plot in which on the horizontal axis there is the time. On the vertical axis, there is the L2 norm of the difference between the high fidelity velocity and the target. And therefore, if the system is getting controlled well, you would expect this curve to go towards the axis, the horizontal axis, y equal to 0. And indeed, in 3 cases out of 4, that's what happens. So what are the 4 curves that are being plotted? So if you look at curves with the same marker, for instance, let's start with this star marker, which are these first 2 cases. These first 2 cases are associated to the case, to the larger gamma equal to 5. And the two different colors are associated to the two different proposals. The green color is associated to proposal A, and the pink color is associated to proposal B. If you look in the figure for these star markers, you will see that more or less they are located here. And you will see that both control laws are able to steer the system velocity to the target one. However, if you decrease the value of gamma to be equal to 1, and now refer to the two lines with two different colors, but with square markers, you will see that only the pink line is going to 0, while the other line, the green line, is oscillating quite drastically. So for a value of gamma which is small enough, we have a numerical confirmation that indeed the former proposal is not able to cope, is not able to control the system, while our proposal, our introduced control law, is also able to handle this when gamma is when the value of the coefficient gamma is small. So this is the introduction to this control. Now let me jump to the second ingredient. The second ingredient is about regularization. And to introduce this regularization, let me copy again one of the formulas that I had in the theorem, in the convergence theorem in the discrete case, and highlight what happens at the denominator. At the denominator, we have an addend which goes as the sum between gamma and C0 times nu. So now let's put ourselves in the case in which both gamma goes to 0, because we would like to control, to have a very little control on the system, but also nu goes to 0, because we would like the flow to have a very high Reynolds number. From this expression in red, it's quite easy to see that this convergence will deteriorate, in the sense that this constant highlighted in red will approach 1. And it is well known that when nu goes to 0, the Navier-Stokes discretization itself, without the control, requires some stabilization or regularization. So in this setting now, our rationale is the following. I've spent a good part of this presentation up to now to tell you that this feedback control is only a slight modification, that is an additional forcing term of the Navier-Stokes equation. So now what we would like to do is to profit from that and try to apply the regularization techniques that were originally developed for the Navier-Stokes equation to this slightly modified system given by the feedback control case. And the first question that we asked ourselves is, how is it that the convergence result that I have recapped here at the top of the slide would change? So would we see any difference in terms of this exponential convergence? And it's hard to give this answer in general. So what we did is to choose a specific regularization, which is this evolve filter relax regularization. The evolve step is a step which requires the same feedback control law as in ingredient number 1, with the exception that I just called the unknown with this u tilde rather than u, because for us it would be an intermediate velocity. The second step is a filter step, which is a regularization in which the intermediate velocity is smoothed out with an operator, with a Laplace operator that depends on a filter with radius delta. And typically, the square of this delta is proportional to the mesh size h. And finally, the third step is a relaxed step that performs a convex combination between the unfiltered or intermediate velocity and the filtered one. where the coefficient of this convex combination is called key. And typically this key is proportional to the time step size, delta t. Since I promised you a practical approach, I highlight here that this is practical in the sense that once you have implemented this evolve step, the two remaining steps are just two additional steps or solves that could be easily added as a post-processing of the solution without touching the code of the evolve part. So now if I go to the convergence analysis in this for this specific evolve filter relax regularization, I can notice, myself and my co-authors, Maria, Trajan, and Claudio, noticed two main differences compared to the previous case without regularization. And these two main differences are highlighted in red in the slide. So now the convergence result is given by the sum of two terms. Let me start from the first addend. In the first addend, the constant that I am now underlining with my red marker is the same as the previous convergence result. But there is a new factor in front of it. This new factor is 1 over 1 minus key. And if key goes to 0, this factor is less than 1. And therefore, this will favor a faster exponential convergence for this first addend, even in the challenging case in which gamma and nu both go to 0. So this first term is the good news. By choosing this coefficient key, we can increase the convergence the convergence speed. However, there is a second addend, and the second addend is the bad news, because in the second addend, in contrast to the first one, notice that in the first addend there is this n at the exponent, while in the second addend there isn't any exponent here. So basically, the second addend is doesn't go to 0 as n increases, and this means that the convergence will reach a plateau, and this plateau will be given basically by the second addend. In this bad news, let's say the good part is that it's true there is this plateau, but the height of the plateau will be proportional to key. And before I told you that key is typically proportional to delta t. So delta t, we often expect it to be small. So overall, combining these two considerations, this has motivated us to deploy an adaptive strategy in which we try to get the best out of the two addends. So the adaptive strategy, in summary, would work like this. At the very first time instances, the goal is we expect the first addend to be very large, because at the very beginning, we expect that the physical velocity is very different from the target one. So we would like to have the help of this multiplicative constant with key strictly positive to guarantee a faster decrease of the first addend. Then, after a few time iterations, we can expect the first addend to be small enough, and therefore will not need anymore the help of this coefficient key. Therefore, once the first addend is small enough, we may revert to key equal to 0, because look at this coefficient here in the first addend. With key equal to 0, we would allow to completely avoid the plateau. So in other words, when n is large enough, we are willing to accept a slightly lower convergence rate of the standard feedback control, the one without this constant 1 over 1 minus key, because the benefit of having this slightly faster convergence is outweighed by the detrimental effect of having this plateau introduced by the second landed. So to convince you that this strategy actually works in practice, we have carried out an experiment, a numerical experiment, in which we set nu and gamma both equal to 10 to the minus 4. So keep in mind that in the previous experiment, the lowest gamma I had tried was 1, or we have tried was 1, while in this case, we're going 4 orders of magnitude less than that. And in the figure on the right, we have a plot in which on the horizontal axis, there is the time. On the vertical axis, there is the distance in the L2 norm between the actual velocity and the target one. And there are 3 curves corresponding to 3 different colors. The blue cyan line corresponds to the case in which we don't use this regularization. So key is equal to 0. That is the case of standard feedback control. The orange line corresponds to the case in which we do have this regularization with the suggested value of key proportional to delta t. And finally, the green line corresponds to this adaptive strategy that I discussed in the previous slide. So if you look at the plot, let's say for, I don't know, t less than 1.5, and you compare the orange line and the light blue one, you see that the orange line, so regularization, is below the light blue line. That is, regularization is helpful in obtaining lower errors. If you look again at this plot for times greater than 2.5 and compare the light blue line to the green one, no, sorry, the green one is afterwards. The orange line to the light blue, light blue one, you see that the orange line reaches a plateau, this plateau that we were expecting from the theory, while the light blue line keeps decreasing. So regularization reaches a plateau, and the standard case keeps the error, allows the error to keep decreasing. So from this picture, this already gives us a motivation to introduce this adaptive strategy. This adaptive strategy is the green line, and as you can see, for small times, it overlaps the orange line. For very large times, it overlaps the light blue line, and for intermediate values of the time, it is in between the case with and without regularization. So overall, we consider this result as a motivation for us to use this adaptive strategy. So in terms of reduced order modeling, I can go a bit quicker on this part because that's you are more used to this part. And with this slide and the next one, the question that we're trying to ask is if we employ regularization, because now I have hopefully convinced you that we need some form of regularization. The best one would be this adaptive strategy. So let's say that by now we agree that we need to employ this regularization for the high fidelity scheme. The next immediate question would be, do we also need to employ it for the reduced order model? And we discussed this question in this work, but we also had discussed a similar question in a previous work that you can find at the bottom of the slide. So basically, we have two choices. If we decide to also regularize the reduced order model, then at the reduced order level, we will have two steps: the evolve, the filter, and the relax step, also at the reduced order level. Instead, if we decide not to employ the regularization at the reduced order level, then we would only be limiting ourselves to the first step, the evolve step. So with the next numerical results, we compare these two options. The axis, the quantities on the axis are the same as before, with the exception that now on the vertical axis there is the error for the reduced velocity rather than the high fidelity one. The orange line corresponds to the case in which we enable regularization for both the high fidelity and the reduced order scheme, while the green line corresponds to the case in which we enable regularization for the high fidelity scheme because we were convinced that we need to do that by the previous numerical results, but not for the ROM. And without spending much more time in further comments, it's quite clear from this plot that the orange line is always below the green line. And furthermore, even the orange line seems to guarantee a monotonic convergence. And therefore, these numerical results are convincing us that it's beneficial for us to introduce regularization also at the reduced order level. And this is consistent with the results that we had also obtained in this previous publication of ours. So this concludes let's say the first two-thirds of the talk. And now for the final set, I have a few extra slides on the second work in collaboration with Anna, Ian, and Trajan. And this second part will be about a different type of regularization technique. And I will give you a brief summary on the work that we did on Leray regularization and approximate deconvolution Leray regularization techniques. So if I went back a couple of slides, the question that I tried to answer there was, if we employ regularization for the high fidelity scheme, do we also need to employ it for the ROM? And with the answer there in our previous work, by now we are convinced that the answer is yes. In this further work with Anna, Ian, and Trajan, we sort of flipped this question around in the sense that, okay, by now we understand that we need some sort of regularization even for the ROM. But is it really necessary that the two regularization at the ROM and at the high fidelity level are the same? Or in principle, could we be more free and decide to use a kind of regularization, a class of regularization techniques at the high fidelity level and a different one at the reduced order level? So since the answer to this question is, since it's beneficial to consider this question only rather than with the whole infrastructure that I have presented before, for these last 8 slides or whatever, I will drop the feedback control term. So we'll simply consider the case in which there is no forcing term. However, we believe that what we achieved in this setting, so the setting without control, can also be extended to the case of feedback control too, since the difference between the two cases, as I have highlighted several times now, is only an additional forcing term. And to highlight the case in which the regularization techniques are different, I will be choosing for the evolve filter Erax regularization for the high fidelity scheme, and 2 other techniques which are not the EFR scheme for the reduced order model. In terms of these regularized reduced order models, in our work we present, or we discuss, say, 2 choices. The first choice is the Leray regularized reduced order model. And in a couple of slides, there will be the second choice, which will be the approximate deconvolution Leray regularized reduced order model. So let me comment first on this one. The Leray ROM is is an approach that dates back to the 30s. And the idea is simple in the sense that we need to replace the nonlinear term in the Navier-Stokes equation from changing it from being u dot grad u to u bar dot grad u, where u bar is a filtered velocity, and the choice of the filter will be up to us. And in practice, we will be using, again, a filter based on a Poisson equation, which has the goal, the goal of this filtering would be to try to increase the smoothness or the regularity of the velocity. So when applied to a ROM, this results in having to find two unknowns: a reduced velocity, or let's say a reduced unfiltered velocity, and a reduced filtered velocity, which are coupled together, which are the result of two coupled equations, in which the first equation is a momentum equation, and the second equation is the equation defining the filter. So you see that there is this Laplacian term with this filter coefficient delta squared. You can, of course, do this efficiently in a fully discrete form at the reduced order level, and this results in two equations which are tightly coupled. The first one that is nonlinear, and the second one which is the evaluation of the filtered velocity. So the advantage of this L-ROM over the standard Galerkin ROM is that filtering can smooth out spurious oscillations that appear in Galerkin ROMs, especially for high Reynolds number flows. However, the disadvantage is that, especially if you're not careful in choosing the coefficient delta square, you may end up with a solution that is over-diffusive. So this disadvantage was the starting point of the work of Anna and Ian in introducing a different regularization technique, which is based on the concept of approximate deconvolution. So the concept of approximate deconvolution would be to start by writing formally the filtered velocity u bar as the application of a filter operator G applied to the unfiltered velocity u. And now if we were to follow the same path as Leray did, the first step would be to replace in the nonlinear term this velocity u with a filtered velocity u bar. So this would be the standard Leray ROM. To add the convolution on top of the standard Leray ROM, the goal would be to replace u bar with something that resembles G, the inverse of G to the minus 1, times applied to u bar. I'm saying that we cannot really use G minus 1 applied to u bar for two reasons. So it will not be an exact deconvolution for two reasons. The first one is that the exact deconvolution would be useless in practice, because by applying first the operator G and then its inverse, we would be going back to the original equation. So we wouldn't have introduced anything new. And the second claim is that this exact deconvolution would also be dangerous, because in practice, G minus 1 amplifies numerical errors. So instead, what we do is an approximate deconvolution. So this A in the acronym stands for approximate. We will not be relying on the exact deconvolution, but rather we'll be introducing an approximate deconvolution operator, capital D, such that D applied to U star is close to U, even though not exactly U. And the rationale or the hope behind this is that if D of U bar is somewhat close to the actual velocity U, then hopefully this would mitigate the over-diffusive behavior, because the nonlinear term would be closer to the nonlinear term of the original equation. In particular, in this work, we choose a specific operator, which in this context is called the Lavrentiev operator, but most probably in other contexts, you know that as Tikhonov regularization. So basically, rather than trying to take the inverse of the operator G, you take the inverse of the sum between G and G plus mu times I, where mu is a regularization coefficient. So overall, this results in the proposal of this new ADL ROM, in which you have three unknowns to find: the reduced velocity, the reduced filtered velocity, and now this approximately deconvolved reduced velocity. These result in a system of three equations, but do not get scared by the fact that we keep adding on, piling on equations, because all of these equations are at the reduced order level. So even these additional equations, the equation that I highlighted now in red, is still an equation of small size, R times R, with matrices of order R times R. So as the final slide of result, I have a couple of results from our publication, in which we choose a benchmark of a backward-facing step for a viscosity that corresponds to a Reynolds number of around 1500. And in choosing in the slides before, one by one, I had to introduce a few more symbols like this delta and mu, and of course the dimension of the reduced space R. So in choosing these values that I reported on the slide and on which I will now comment, the expressed goal was to make it as hard as possible for the ADL ROM. And how is it that we can make it as challenging as possible for our new ROM? The first input that we can set is R equal to 10, let's say a small number of POD modes. This is attractive because it results in large speedups that in our setting and for our implementation were of the order of thousands. So very few POD modes may result in a very small, in a potentially inaccurate basis or inaccurate representation of the velocity. Then to pile on challenges, we will choose delta equal to 0.6, which for us is large, which means that the Leray ROM, so the one that I claimed was over-diffusive, will be very much over-diffusive in the sense that this filtering radius will be very, very large. So the Leray ROM will smooth out very much the solution. And now this approximate deconvolution should try to recover a less smooth or a less diffusive solution. So by choosing delta very large, we are making it very hard for the ADL ROM to give us good result. And finally, this coefficient mu that appears in the definition of this Lavrentiev operator or Tikhonov operator needs to be chosen as well. So we don't have right now a clear-cut way of choosing it. So what we did, what especially Anna had to do, was to have some tuning to choose this value, and it turned out that 0.06 was a reasonable value. So now to comment on this result, we have on the left a plot of the kinetic energy on the vertical axis with respect to time. And in this plot, you have four curves. The black one is the projection of the finite element solution. The red one is the standard Galerkin ROM. The green one is the Leray ROM. And finally, the blue curve is our proposed ADL ROM. So overall, you see that the red line seems to overestimate or seems to have a trend in which the kinetic energy keeps increasing. That's the Galerkin ROM. The green line seems to have a trend in which the kinetic energy gets smaller and smaller, and that's due to the over-diffusivity of the Leray proposal. And our proposal, the blue line, even though it's not perfect, it doesn't perfectly overlap the black line, is at the very least is the closest one to the black line. In the picture that you have on the right, instead, you have a plot of the relative errors over time in the L2 norm. And again, the colors have the same meaning as in the previous picture. And again, I want to highlight that if I look at the final time, the blue curve is the one that achieves the smallest error. So with this, the summary is our goal was to introduce a flow control strategy for turbulent flows, relying on reduced order modeling. The talk was divided into parts. The first part, and in the first associated paper, which is paper number 1 here at the bottom, we introduced novel feedback control law and adaptive regularization strategy based on evolve filter relax regularization. In the second part, which is associated to the second paper, we introduced a novel regularized ROM based on approximate deconvolution reduced order model. So all of this is set in a longer term goal of trying to control turbulent flows at higher Reynolds numbers. And all of this was also done thanks to funding by the European Commission within the ARIA project and by the European Union in the Romeo project. So with this, I thank you for your attention.
Very nice, Francesco. Thank you. This has been thank you. This has been a fantastic presentation. Thank you. If there are any questions for Francesco, please raise your hand. Ping Xuan. So go ahead.
Yeah, Francesco, I have a question about the adaptive EFR. What's the criteria you use to switch from non-EFR to EFR?
So let's see. Let's go back to this slide. Where was it? This slide here. So I think that right now we don't have like a very refined criterion. Our criterion is very simple. So I think that the simplest criteria that you have in mind is that a priori you fix a number of instances in which you're allowed to keep EFR on, or you have a look at the norm of the difference between the current velocity and the target one and decide if that norm is small enough, then I'm happy to switch the additional help off, or if it is still big, I'll keep the additional key enabled. So those are the two simplest criteria that come to mind. But in principle, you could also do something more refined. For instance, you could also look at how big is the second add, and the issue is that the constant appearing in this sum are difficult to quantify, so it's not immediately evident how to rely on this second add and to use that in switching from one configuration to the other.
I see. Thank you.
Welcome.
Thank you. Faye, do you want to ask a question?
Yes. Hi. Hi, Francisco. Thank you very much for the nice talk. Can you turn to page 25? I'm very curious about your regularization for the deconvolution part. I think because you have explained here very well, but I still want to confirm with you minor details.
Yes.
So you mentioned that for selection of the parameter mu, with some tuning, do you have more insight about how this mu depend on like R or delta, or in some other way like the condition number of your G over there?
So we noticed that there was a dependence on between mu and delta, I think. I don't think that we tried for many different values of R, but yeah, I could expect that there is some dependence on R as well. And honestly, the reason we didn't do that is because this task is very boring, in the sense that we haven't found a way to do this in a automated or algorithmic way. So somehow the best approach that we had to use was basically try out different values and pick out and pick maybe on a smaller time window, not this one that you're seeing right now, the one that seemed to have the best performance. So if you have ideas on a way to make this more to make this algorithmically robust, I think it would be great for this work, but also for many other works, because I think that my co-authors here could agree with me that this part is a part that right now is still manual and would benefit for some more mathematical guidance.
And to follow up, I think that this is so Francesco just explained it very well. I think that that's where we stand right now. But it's also true that Francesco, Anna, Ian, and I, so we're working on a numerical analysis follow-up paper. And so what we plan to do is to look, so proving error bounds. I think that that's important, but I think that the most important thing is the practical aspect. That's something we haven't done yet, but it would be interesting to see if we could use the error bounds to find parameter scaling. I think that really this would justify the need for numerical analysis in practical calculations. Finite element people, so classical methods, they always do this, but we haven't done that. So it would be interesting to see if we could leverage the numerical analysis to get those parameters. So that's work in progress. So Francesco and the rest, so we're working on it. We stopped before the Christmas break. So now we have to pick it up. Okay, so that's where we stand.
I see, great. The reason I'm asking here is because I'm also working on some simpler, not getting the PD, just deconvolution itself for the regularization part. There is some method like Tikhonov, if the basis changes, the Tikhonov may have trouble. So we have some so-called, also in line with your earlier part about adaptive regularization. Yeah, okay. I can talk more about that later.
Okay, yeah, great.
Mm-hmm. Absolutely. Thank you. Absolutely. That would be great.
Yeah, great. Thank you.
Thanks, Faye. This was a great question. Anybody else? Anybody has any other questions for Francesco? I don't see any raised hands. There were a couple of very good questions. You can always reach out to Francesco. He's very happy to answer his emails. So please reach out to him if you have any questions. Thank you. Thank you all for coming, and thank you, Francesco, for a really fantastic talk. I really learned a lot today. So thank you for that. And we'll see everyone at the next so next Tuesday, the next installment in our NAGRAM seminar. Thank you.
Thank you. See you next Tuesday.
See.
Bye.
Bye.